This lecture is going to be on conditionals and biconditionals, the next section in our chunk of logic. A conditional sentence looks like P with some arrows and a Q, and it's read P implies Q, or if P then Q. P is known as the antecedent and Q is the consequence, but I never call them those because it's kind of stupid. And it's easier just to say the if part and the then part, or the P part and the Q part. Antecedent and consequence. Logically, the consequence isn't always a consequence, as you'll see when we start talking about the logic. So I think that part's kind of misleading. Anyway, so this is true when P is false or when Q is true. So it's equivalent to the expression tilde P or Q. So beware the trap of English. And what I mean by that is, if I say, if I have red hair, then John has 4 legs. Now clearly the color of my hair has nothing to do with John's legs, but this would be, I can't remember what I said, this would be a true statement because I don't have whatever color hair I said I had. Since the first part is false, I have the P part is false, and I don't give a shit what the Q is because this part is false. So we can move on. You may say, well, but Megan, you don't have purple hair or green hair, whatever the hell you said a minute ago. That doesn't matter. It's the conditional sentence, it's the conditional proposition that would be true. The individual parts could be false, and the whole thing could still be true. The truth table for this, then, looks like this. The only time that P implies Q is going to be false is if the P part is true and the Q part is false. Think about it this way. If I were to say, if you mow my grass, that's a P, then I will give you $50. That's the Q. Well, if you mow my grass and I give you $50, you're happy. All's good with the world. If you mow my grass and I don't give you $50, you're going to be pissed. So that's the false. If you don't mow my grass, then it doesn't really matter what happens because you didn't really earn the money anyway. So either way, you're happy. Well, you probably think you should mow my grass. If you think about the mowing grass example, this kind of makes a little bit more sense. So definition. We can take conditional statements and play with them. And we have names for the different games we've played. The converse of P implies Q is Q implies P. The contrapositive of P implies Q is not Q implies not P. Now let me be very clear. P implies Q is not the same thing as Q implies P. Good example. If I'm in a sorority, then I'm a girl. If I'm a girl, then I'm in a sorority. The first part could be true. The second part doesn't make any sense. Whereas the contrapositive, if I'm a girl, if I'm in a sorority, did I say fraternity? If I'm in a sorority, then I'm a girl. If I'm not a girl, then I'm not in a sorority. That is equivalent to the original statement. There are some language issues. There are some words that you can look at and go, oops, didn't mean to screw about that. Other ways of saying if P then Q. I sometimes get all mixed up with these anyway, and I'll tend to stop and think about it and go back and think about the lawnmower example and whether I'd be pissed or not. So it's easier to put it in those terms. Because then if I start saying P is sufficient for Q, it's like, okay, mowing my grass is sufficient for you to get $50. Okay. Mowing my grass only if I'm willing to give you $50. $50 if you mow my grass. $50 whenever you mow my grass. Getting $50 is necessary for you to mow my grass. $50 when you mow my grass. See, kind of gets monotonous, but sometimes it's easier just to think about it in terms of the grass example. Example. A sequence is bounded whenever it is convergent. Okay, so if we think about that, whenever it's convergent, so the whenever part gives me the P part, right? Whenever P. Yeah, okay, good. So it is convergent is the if part, is the P part, is the antecedent. Bounded is the consequence, or is the Q part. So if I were to say, so this is the same thing as saying, if a sequence is convergent, then it is bounded. The converse is, if a sequence is bounded, then it's convergent. The Contrapositive would be if it is not bounded, then it is not convergent. Another thing we can look at are biconditionals when they go both ways. Two propositions P and Q. We have the biconditional sentence P if and only if Q. If P then Q and if Q then P. It means it goes both ways. This is the same as saying P equals Q in terms of logic. Other words for P if and only if Q. We have P if but only if Q. So it's kind of like all those that language we had before when they squish them together, right? So you have both terms. P is necessary and sufficient for Q. P is equivalent to Q. It's the same thing. Grossly-less theorem. P implies Q is the same thing as not P or Q. Okay, we said that at the beginning. If I want to say P if and only if Q, that's equivalent to P implies Q and Q implies P. So if we have to prove this, which we will later on, we're going to have to do both parts. If we negate P implies Q, well, we're negating an or, so it's going to become an and each part will be negated, and negative P is a positive P, or the P. Negative Q is negative Q. And if I want to negate an and, it would be the same thing as saying P implies not Q. I don't usually use that theorem that much. So let's look at some examples, problems. In these sentences, I want to say what's the P part, what's the Q part, and whether the statement is true or false. So if squares have 3 sides, then triangles have 4 sides. That's the P part. Squares have 3 sides. Q is triangles have 4 sides. Since P is false, don't care about Q. The entire statement is true. Let's try another one. B divides 3 only if B divides 9. Okay, so the P part is B divides 3, and the Q part is B divides 9. Now I have to think a little bit harder now, because I don't know what B is. So I need to think about this. Case 1, if P is false, okay, well, then I don't care, the statement is true. Because P implies Q, if the P part is false, the entire statement is true. Case 2, but I already said that. If P is true, well, let's think about it. If P is true, that means B divides 3, which means B has to be either 1 or 3. And 1 and 3 both divides 9. So Q is true, this statement is true. One of the things you have to be able to do is take a sentence and rewrite it mathematically, to some extent. So we've got if n is prime, then n equals 2 or n equals odd. Or n is odd. Oh, that's weird. N is prime is the P part. Q is that whole n equals 2 or n is odd. I keep saying equal. Now, but that has 2 substatements, so we really don't want to call it Q. We want to call it something different. We've got 2 statements. N is 2, n is odd. Let's call one of them R and the other one S. So now this sentence becomes P implies parentheses R or S. Okay, let's try another one. S is compact if and only if S is closed and bounded. IFF is how mathematicians spell if and only if. It's not, I didn't misspell if, that really is IFF. S is compact. What the hell is compact? I don't know. I didn't ask you to prove it was, say it was true or false. I just wanted you to tell me, rewrite it as mathematics. So we've got a sentence here. S is compact. If and only if, all that crap. So we have a P and we have an S. If and only if. Now this Q is 2 parts. We have S is closed and we have S is bounded. So I'm going to call one of them R. Why don't we use S this time since S is actually part of the sentence. We'll call this T. So I have P if and only if R and T. So that's what's meant by let's rewrite this in terms of mathematics. Now we need to do this, be able to take something that's written in crappy English, mathematics, whatever, and then write it logically so we can be exact. In mathematics, we are exact. Unlike science, where they're kind of wishy-washy. Ooh, don't tell anybody I said that. Mathematics, we have this is true, this is false, there's no fuzziness. Okay. So, hopefully you can do the homework. That's all for this section. Have a great day.